Hi, so welcome to lecture 6. This lecture is going to begin our study of calculus. In the prior 2 weeks, prior lectures, we've learned about the limiting process. That's kind of the bridge between pre-cal and calculus. We had to spend time on it. And it's because the two fundamental notions in calculus depend on limits. And we're beginning the study of one of those notions. So maybe I'll just write that out so you can remember this for later when you tell people about taking calculus. Calculus was originally two different branches of what turns out to be the same subject. The first branch being differentiable calculus, and the second branch being what's called integral calculus. They were actually developed separate from each other, but they turn out to be two sides to the same coin. And these two topics together make a calculus. And the majority of, well, not majority, but we're going to spend a lot of time talking about differentiable calculus. And that's what we're starting today. Okay. Now, the idea behind, or like the motivating notion for differentiable calculus and this idea of a derivative is a thing called a tangent line. Okay, so motivation for differentiable calculus is the tangent line. We don't know what that is, but we're going to learn today. Okay. So to introduce the idea of a tangent line, we should consider maybe some function. Okay. So, and for now, let's just assume that this function is smooth and differentiable, which we don't know what that means yet, but smooth. There's no crimps in the graph of the function, and it's continuous. Okay, and continuous, we should know what that means. There's no hops anywhere, no discontinuities, and there could be like very sharp points on the graph, but we're going to say smooth and avoid those sharp points on the graph. So one such function could look like this. Okay. We'll just call this f of x. Okay. Now, this function could be modeling something. Okay. And because I'm a data scientist and I research machine learning types of things, I'll kind of formulate it in that way. Okay, so maybe something like, suppose let's say f of x is measuring the cost, which you can think of as maybe, I don't want to use the word, but accuracy maybe, of a model. maybe something like a self-driving car. Okay. Okay. So how would this model work? What is this measuring? Well, for example, like you have like a car that's driving around and it takes as input like some picture in front of it, right? And then it has a few choices to make. It can brake, it can turn left, it can speed up, these types of things. And based off of those choices, things happen, right? And if they're bad, right, we want to penalize that model, that self-driving car. We don't want it to run into a pedestrian. We want it to, if it sees a pedestrian, we want it to know to brake immediately if they're like right in front of it, right? So one way of measuring how this machine learning model is performing is by giving it a cost function, okay? Where the input to this cost function are the knobs and weights of how the car chooses to act. Like it takes as input some like picture, and then based off of X, it determines whether or not to make an action. And based off of that action, it's either rewarded for doing good or penalized for doing bad, right? Does that kind of make sense? So maybe that cost function as a function of X, where X is the value that's like determining which way to go based off of an image, right? Looks something like this, right? Suppose it looks like that, right? And again, the thing is doing bad when its cost is really high, right? Thing is doing bad, the car is doing bad when it makes a left turn and it runs into a car, it gets penalized, and that's what this function is modeling. Okay. So what would be the goal of this, right? Like if this is the cost function describing how well it's doing at not hitting people and like driving correctly in the right lane based off of this parameter, right? We don't want the cost to be high, right? Another way of another term often used is a loss function. So we want there's a loss function and it's really high when we're doing bad. So what we want is we want to somehow find minimums of that thing, right? Like if we find an X where this function is low, then the model, the car is driving better, right? Again, the thing that determines what it does is that X, right? And the cost it incurs for making an action is this function. Again, I'm oversimplifying a lot of things, but that's kind of the main idea, right? So what we would like to do is to maybe find minimums of this cost function, right? Like if we can find an X where this is minimum, we know that the car is doing the best it can, right? If we're up there, right, it's not doing very well. It could do better, right? It could do better if we go down. If it's like over there, it could do better, right? So maybe like, I don't know, we built our model and we want to start training it to do better, to learn. We want the machine to learn to do better based off of where it's at, right? So this is this notion of like machine learning. We want to have our car learn to not do the wrong choices, right? Based off of the data that it's using. So when we start this model out, we really don't have any idea what the appropriate X is, right? And again, X is the thing that's determining whether we brake, turn left, speed up, that kind of stuff, right? We don't know that ahead of time. There's so many possibilities. There's no way that we could ever program every case in there, like dog and road, child and road, like all these things. Like there's no way that we could ever program that. The best that we can do is make a guess and then use information about this function to make a better guess next time. So maybe when we start the model out, we start like right here. I'll call this like, I don't know, what do I want to call it? X subscript 9. Okay. Right. And luckily we can simulate driving cars with a computer, and like we can say, this is the parameter that's going to determine how it acts as it's driving. And then we throw that into a program and we simulate driving around, viewing different things, and we see how it does, right? So that simulation is going to tell us, it's going to give us information about what the cost function looks like around there, right? Like suppose we don't know what it looks like. We just know that it's measuring how well that choice of like the instructions basically are doing, right? Now, it would be nice if there was something about that function that could tell us where to go. Like looking at it, so this is the point that we're at right now. This is f at x subscript 0. So that point is this pair, right? It would be nice if there was something that we could, like something that the function could tell us on where to go. Looking at it, if we want to find lower values of f, which direction do we need to go? Down, but how do we know to go down? Like we're looking at go left though, right? Yeah. We're going to pick a new x, but the idea is to go down. So what about that function could tell us that, right? Or maybe I'll make another guess in red. Hopefully it picks up on the camera. Like maybe I guess like right here. I'll call this like x1 or something. Then this is like f at x1, and then that point right there is x1 comma f of x1. So if that's our guess, right, do we need to increase x or decrease x to make the function go down? Well, increase x, which will make the function go down, right? Like if we move this way a little bit, we're going this way. Yeah, so this would increase, but the function would decrease. Notice how I'm doing this motion, right? I'm kind of hinting at something. It's almost like around these guesses, if we approximate the function by a line, that line is going to tell us where to move, right? Like with lines, we know something called slope, right? We know slopes of lines, right? So like, I just draw any line like that, y equals like x plus 1 or something. That has positive slope, right? And then like something like that, like maybe h equals to, what is that, like negative x plus 3 or something. That is negative slope, right? So looking at these functions, it's really easy to tell, like if we're trying to like go uphill or downhill and we're like right here, and we want to go up, the slope is positive, which means we need to go that way. If we want to go down, since the slope is positive, we go in the opposite direction. So it's easy to tell with lines, right? So what if we approximate that thing around those points by some small line? Like for example, like let me draw such a line. So really close around here, I'm just going to make a line right there and see what it tells me, right? Where it just touches the graph of that function at that point. It's a line the function might like dip down all over the place. It doesn't matter, but close to it, it's like just touching at that point and it's a line, right? Now imagine that you didn't know this line. Like we just didn't know it. And we made a guess as to where the parameter that controls the car is going to start. And we want to minimize this function, which is telling us how well the thing is doing. If we made a guess right here, and we knew the slope of this line, we would know to go this way, okay? The slope is positive, which means if we increase, we're going up the function. Since the slope is positive and we want to decrease, we need to go left to decrease on that function f. And then same thing here, right? Look at a tangent line to that point, right there. Again, I'm trying not to ruin my red marker, so I'm not actually drawing it on the black, but you get the idea. Right, again, if we didn't know the true curve, wouldn't that line right there, like that approximate the function at that point, the slope of it's negative, right? So if we didn't know anything about the function and we knew the slope of that line, and we're right there, since the slope is negative, we would know to go downhill, we need to increase our guess. Does that kind of make sense? So maybe actually, what happens is something like this. Like we make a guess, we are able to somehow find the slope of that line right there. It's positive. So that means we go that way. And then we land right there. And then we know the slope of the line that's touching the graph at that point up there. It's negative, so we go this way, right? So then we land somewhere else. Maybe we land like right here. And I'll call this like x2. So 0, 1, 2. We're bouncing around, Okay. So what would the line right there? So that point is what? So a line approximating that function right there, just really close. Right, just really close to that point. What does that line look like? Exactly. If the line is flattened out like that, what does that tell us about the curve right there, around that little, around this guess? Imagine we don't know the curve everywhere. We just know around there, right? And that line that's just touching is flat. That means what? We're kind of at we're at like a little cusp. Transition, that's one thing that we can gain from it. I like that. But we know that we're at like a little, we're at either this, right? Possibly a local minimum. I mean, I say local because maybe we could have got stuck right there. That would also have a flat line. In fact, that line right there would be flat. That line right there would be flat. So what I'm hinting at is that if we didn't know where the minimums were on there, maybe we could just, if we knew the slopes of the lines that touch the graph at that point, if we make a guess, we can make a new guess, guess, and then whenever that line is flat, that's the best that we can hope for. We found something that's in like maybe a little bowl, right? Which means that we can automate this process. Whenever you can use information to make a new guess, and then if you have the same information to make another new guess, we can automate this process over and over again. It's called an iterative method. And this iterative method will on its own find one of these little cusps. And that's precisely what machine learning is. There's a thing that determines the behavior, the choices. It's typically called a weight. And based off of the image, it weights like whether or not to go this way, that way, brake, or whatever. And there's some function that's modeling how well it's making the correct choices, because we can simulate this like model, like with the computer, and we can get the correct choices. So we know the correct choices, and we just see whether or not it's doing those correct choices, right? And it gets penalized whenever it doesn't. And we form this function called f, sometimes called a loss function, sometimes called a cost function. And then the next thing that we did was use only really the slope of the line touching the graph to move back and forth until we found something. So this is how I like to motivate the usefulness of these things. And this is not just with a machine learning like loss function. Like this could be any function that's measuring growth or behavior, like in biology, in chemistry. Finding these little cusps, which are called local extreme or local minimum, local maximum, has applications because you want to know those values where it's like things are extreme in behavior, right? If like there's absolutely no species of this rabbit left, then you want to know where that occurs, right? And how would you know that? Well, if you have a function modeling it, it doesn't pass through here, you know that there's a minimum value somewhere in the number of rabbits. When does that happen? What parameters make that happen? This could be like time in that case. This could be like temperature, right? For like if looking at like sea level rise, right? Like this could be some function of temperature. And we want to know like at what temperatures do these extremes happen? And all we need to do that is the ability to find the slopes of those lines, right? If we knew the slopes of those lines, we could make a guess and then we can just move in the opposite direction of the guess to go down the function. Or if we wanted to go up the function, we would go in the same direction as the slope of those lines there. Right? I kind of chose minimum because it's related to machine learning, but sometimes you want to maximize things. So you make a guess, look at the slope, it's positive, go that way. Okay. If you're curious about what this process is called, it's called gradient descent. The gradient is a multivariable version of the derivative. So it turns out that that thing called the derivative is what's going to tell us those slopes. Not only the sign of it, like is it positive or negative, but how positive it is or how negative it is. That's what the derivative is going to tell us. Okay. So hopefully that was motivating. It is admittedly taught differently in your textbook and on most lectures you'll see, but this is how I like to motivate it as a tool to use to move around functions where we don't know what the function looks like and to find things out about it. Okay, so there's that picture. Maybe I can squeeze in. Yeah, I think I can squeeze it in over here. Try to do it very big. So now we're going to derive a way of finding that value. Now, do we remember? Well, actually, I'll set it up first. So there's my function. Okay, looks like that. It's probably too mellow. Actually, here's my function. There. And suppose we're at that case where we made our initial guess, right? And we have to somehow figure out a way to find an approximate value to this line. It's just touching the curve right there. Okay, so as before, let's make this guess. I'm just going to call it X for now, without any subscript. Okay. Maybe I'll scoot it over a little bit. It'll make it easier to draw. Right there, maybe. F at that guess. Okay. All right, so the way that we're going to do this is by approximating it with a line where we know 2 points on the function. Right, so for example, if we know the function, we're going to use that we can like evaluate the function at different points. Like let's scoot x a little bit this way. So this would be like x plus delta h. Now, what is that delta h? It's just fancy notation that means that it's some quantity. Actually, yeah, I'll use x instead because your textbook uses x, whatever. And then just here, just note that delta x is just some positive number. Whenever you see delta, by the way, in calculus, it's typically going to refer to a change, like when things are changing, right? So that right there is just saying we're changing x by this value. Okay, so hopefully y'all can see that. All right, so now that we made this this change, so we are allowed to evaluate the function at any guess we want. Okay, so in particular, we change or perturb x by a little amount, and then we can evaluate the function at that value. Yeah. Now, that means if we can evaluate the function at that value, and we can evaluate the function at this value, we have 2 points. And we should be able to figure out the equation of a line passing through those 2 points, right? So what are the points? I'll call, I'm not going to be able to fit the actual labels there, so I'm going to say this, like P1, P2. Okay, just, I would like to write it like that, but I can't. So what is P1? That is equal to the point x, comma, f of x, and what is P2? It's equal to x plus delta x, comma, f of x plus delta x. Okay, so first we're good. So we have 2 points. Okay, so there's a line passing through those 2 points, right? And that line looks like this. Let me make it a little bit steeper so it doesn't look so much like a line. Hold on. Like that or something. Okay. This is just for demonstration purposes. Right? So there's 2 points, and there's some line that passes through them. Like that, right? So doesn't that kind of look like what we wanted? It's like almost there, right? It would be an approximate, like this, the slope of this thing would be an approximate, so that's slope. Not exact, but it's approximately there, right? So what is the slope of that line passing through those 2 points? It's positive, but there's also a formula for it. Almost. I'll just remind you real fast that just recall that the slope m is equal to y2 minus y1 all over x2 minus x1, right? So that saying rise over run, or I think that's what they say with that. Okay. So I'm going to say that the slope of this line, I'm going to denote it by this. M1 is this slope. By the way, this line here is called a secant line, and you'll read that in your textbook. It's the name of that thing. I don't ever use that term, but you'll see that name in your textbook. Okay, so we know all the information to calculate M1 because we know that and that, we know that and that, right? We're assuming that we know that value, we can evaluate the function, and we just move it by a little bit, and we can also evaluate the function. So hopefully you've written that down because I'm about to erase it. I need some room. So M1 is equal to y2 minus y1 over x2 minus x1, right? But we just replace them by what they are in those points. So this will be f of x plus delta x. So it's like y2 minus y1 all over x2 minus x1. What's that quantity minus that quantity? This minus that. Mm-hmm. Delta x, just a.
That doesn't work on the top.
Oh, we're evaluating the function there, right? So we don't know what the function does to it, but it's probably not going to get rid of it. But just these numbers here, yeah, that's the same number as that, and we can just get rid of it. Okay. So that's an approximation to what we want to have. Right? We want, just suppose we want to do machine learning, we want to find the signs of those tangents or the slopes of those lines that are touching the graph. So that was our first guess, right? Let's make delta x smaller, right? Like delta x is how much we added on there, right? Let's make it a lot smaller. Let's divide it by like 1,000 or something. All right, so if we make delta x smaller by doing that, like maybe I'll say like, I'll call it delta x prime is equal to delta x divided by like 1,000. So we're like 1,000th of the way from there to there, okay? So those p's now, let's just say it's like right here. So this would be x plus delta x prime or something. The new one, the very small one. We just added like a little tiny bit to it, right? We're closer now, right? Now let's look at that line connecting those points. Oh, I'm going to ruin my red mark. Okay. Now, look at that red line. Look at that blue line. They're like drawn differently, but you get the idea. That slope of this line is a much better approximation to the slope of the line touching that graph at that point. And again, I said it earlier, but maybe you didn't like catch on to how important it is. We want to maybe approximate the function as a line really close to that point, right? And that's exactly what we're doing. We're approximating that line that's touching the graph, or no, we're approximating the function with a line close to the point x comma f of x. So what is that slope? I'll call it M2. Well, it's the same type of thing. It's f of x plus, in this case, delta x divided by like 1,000. That's what delta prime x is. And then here. And remember that we have 2 points now, just like before. Is that clear? Or did I move too fast? So that's better, right? What about if we divided delta x by like 1 billion? Then we'd be even closer to x, and then we'd have a better approximation to the slope of the line touching that curve at that point. Maybe we divide by 10 billion. Try it again. Maybe we divide by 2 to the power of 1 billion. Try it again. Try it again. Always adding smaller and smaller amounts. This formula is not going to change. But what's happening as we increment this process, the thing that we're adding to the x in question, that is getting smaller and smaller and smaller. The smaller that it gets, the closer we are to finding the slope of the line touching that point on that graph. Okay. Well, look what's happening. When we're far away, it's not behaving like that function. But when we add a smaller amount and make the points on the graph closer, when we connect those points by a line, it's a better approximation. And if they're like basically on top of each other, and we connect a line between them and then look at the slope, that's going to be a line touching that curve at a point. Yeah. Well, that's why we had the previous lectures. So the comment was, we can get as close as we'd like, but we would never like get there, right? Because we're always actually adding a non-zero number, right? But so we can't like evaluate this thing with delta x equal to 0. Like we can't do that. We can just make it as small as we want. What does this remind you of? It's a limit, right? It's a limit. Like how many times have we encountered looking at a function where we want to know the behavior of that function as we approach a value where you have division by 0, right? Like we have these like removable discontinuities where it's like for example, I think the best one is from one of our very first lectures, and it was a curve that looked like this. It was a parabola with a removable discontinuity at like 2 or something like that. Okay. Now we could never plug in 2 to this because it would have resulted in division by 0. I forget what the exact form was, right? But there was we could like factor out an x minus 2, and it was like this is what we ended up with, right? But still, as we approach 2 from the right and the left, the function goes somewhere, right? It still goes somewhere. Like if the limit exists as x goes to 2 for this function, that function is basically on top of that point right there. Which means that even though we can't plug in 0 to add here, which would be 0 division over here, right? We can still look at the behavior as this quantity that we're adding and dividing by gets smaller and smaller and goes to 0. And that's precisely what the derivative of f is. Definition. Need more space. Okay. All right. So the derivative of a function f at x is the following limit provided it exists. Now remember, not all limits exist. So it's the limit as the change in x goes to 0 of this quotient here, this ratio, which is called the difference quotient, which you might have seen in like pre-calc. And that's if this exists. Okay. And it's kind of what we're hinting at, right? We added this big of an x, and then we made a smaller x to add to delta x, make a smaller one, smaller one. If that limit exists, that's actually, I should write that down for sure. So I can get rid of this picture now. Okay, so I'll elaborate on this definition. So if this limit exists, we use the notation there's a few different ways of writing it. One of the most common is f prime. Let's write it out one more time. Okay. But we also use that notation.
So what makes the f prime different from the negative?
It's just notation. It's a way of representing the derivative. This is a common notation that you'll see. So f prime is just equal to that limit if the limit exists. So if the limit exists, you can just write the derivative at that point x by that. Okay. We also use this notation. I guess I'll write it out again, just to emphasize that point. So when we start off, like just maybe 1 or 2 lectures, I will primarily use f prime to denote that limit. However, I will, in the weeks following that, use this notation as well. This is read df dx, the derivative of f with respect to x. Okay, and I should maybe emphasize at a point, right? However, if that limit happens to exist for all x in the domain, then you can write a new function actually. It's the derivative as a function. Okay. So for now though, I suppose just focus in on f prime. I don't want to confuse it with this other notation just yet. So notation, and then one important fact, very important fact. F prime is the slope of the line tangent to the graph of f at the point x comma f(x). It's precisely what we wanted. Okay. All right, so the definition requires us to compute a limit if we're going to find it, right? Now, computationally, with like a calculator or with a program, you can't take limits like that, but you can approximate them. You just replace the limit by just a really small delta x, and then it's basically the derivative. But there are some caveats to that. Okay, so this is the tool that we have to find these things. So let's do an example maybe. Okay. And we'll start really simple. So find the derivative of f of x equals to x squared at x equals to okay. So that's that parabola. And again, a lot of times you're just going to encounter so many problems where it's like calculate the derivative. But you have to always remember what it's telling you. As soon as you find that value, you know something about that the curve of that function at that point. Question?
Yes. Once we find out what that means.
It means exactly what I just said. It tells us the behavior of the function around that point.
Yeah, but what do we do with the information?
As before, we can use it to move around the function. Because many times, most problems, you won't know what the function looks like. And you want to find minimums and maximums. Right? So you can make a guess and then use the derivative to move somewhere. But that's just one application. It also tells you rate of change. And so think of it like this. Like to answer your question in a physical sciences point of view, suppose like, and I'll tie it in with this example as well. Suppose like you're modeling like distance over time, right? There's time, there's distance, okay? And the function that models it is the parabola on the positive side of the y-axis. Okay, so at t is equal to 1, it's like off a little bit. The function's value is 1, right? What is velocity defined as? So average velocity speed is always non-negative. Velocity can also be negative. You get negative velocities. It's just your distance minus your old distance, time minus old time. It's your change in distance over your change in time, right? Think about it like meters per second, right? That's the measurement for velocity. So change in distance over change in time. Okay, so that's what velocity is, right? But this is average velocity, right? That's like, that's not really important in a lot of cases, right? So like, with like that definition of average velocity, like imagine, I'll try my best. I live pretty close. I'm gonna try to model my time to UHD in my house. So here's like time and then distance from my house. And at time equals 0 before I leave my house, I'm at 0 meters away from my house. Okay, so I walk out my door, so I'm like a little bit far away. And then I like sit in my car for a second, I reverse like that. And then kind of turn my wheel, I drive, I hit a stop sign. And then I briefly hop on like a major road, and then I get off, right? So this is like my drive to campus, right? So like, this could be like I'll say like 2 meters away, and then maybe like 150 meters away. If I were to compute the average velocity over that, it's like, maybe it takes me like, I don't know how many seconds, but like that slope right there, whatever its numerical value is not indicative of anything about my velocity in there when I had to get on the freeway. What we need is a way to measure the paradoxical statement instantaneous velocity. If average velocity is the slope of the line connecting the 2 points on the graph, you can think of instantaneous velocity as the slope of the line touching the graph at a single point. So I'm going to change this to be like 2 to reference that problem there. So this right here, the slope of that line is my instantaneous velocity at that time t. It's my velocity as when I'm like on the freeway or whatever, okay? That's like another application. And we're going to discuss many different applications of knowing that quantity. Because again, I can't emphasize it enough. It tells you the behavior of the function, the graph of the function around that point. Behavior tells us everything. It tells us where we're going, where we came from, how fast we're going, how slow we like got there. It tells us everything about what the function is describing. So it tells us how to move around it. So back to this problem. Now, we're going to do this by actually computing that limit. Okay. So these have to recall the definition. F prime at 2. So in that difference quotient, just replace x by 2 everywhere. This is going to be the limit. Hopefully it exists as the change in x goes to 0. Of f of 2 plus the change in x minus f of 2 all over change in x. If we can figure out what that value is, that numerical value is, it'll be the slope of that line right there. Okay. So another way of writing this be the limit as change in x goes to 0. Now I know what f is in this case. I know exactly what it looks like. Okay. So instead of x, I'm going to write 2 plus delta x all squared right there. So minus, and then f of 2, I just plug in a 2 into that function, it's 4. Okay. Hang on. Okay, so now I'm going to do some algebra and expand out that quadratic term. So 2 plus delta x squared, for those of you that it's been a while since you've had algebra, but I'll just work it out for you just in case. It's the distributive rule, right? 2 times 2, 4 plus 2 delta x, that times that, plus 2 delta x, and then finally plus delta x all squared. combine my terms. And this is what it ends up being. All right, so that's what I'm going to write out after the limit. So the limit as change in x goes to 0. The first piece is that 4 plus 4 times delta x plus delta x all squared minus 4 over delta x. Notice 4 minus 4 goes away. So and we're still trying to evaluate the limit, but at least the 4's go away. Yeah. And then finally, I see a common factor of delta x, which I can divide out. But I'll write up a step just so you see it. So this can be limit delta x is 0, factor out a delta x in the numerator. And you're left with 4 plus delta x inside. And that's all being divided by delta x. The delta x's can divide out. That's just a 1 right there. And we're left with the limit as delta x goes to 0 of 4 plus delta x. What's that limit? Positive 4. Right, there's no negative term in there, but yeah, it's just because that goes to 0, right? We can just plug it in. That's it. So the slope of this line tangent to this curve, so this is our function, is 4. If this was modeling like driving or something, distance over time, then after 2 seconds, the person would be going 4 meters per second. Yeah.
When you showed us the last equation, df over dx, wouldn't it just be 2?
No, they mean the same thing. Df dx is just notation that represents the same thing as the derivative. But we're going to save that until we get to functions. Okay. Now, I think that this seems a little bit scary right here because there's a lot of algebra, lots of places to make mistakes. However, we are going to encounter next time rules that will make this easy. Like I didn't have to do that to know the derivative of this function at 2 is going to be 4. I didn't have to do that at all. I could do it in my head immediately because there's a very simple rule for calculating derivatives of polynomials. Okay. In fact, you could replace 2 by x everywhere here and you would find the rule. For example, let's just go ahead and do that. Okay? Just so you can see that there is a rule that you could have used. All right, so x, let's write that rule. That is x. So now x is a variable, right? It's not a numerical value. We're just testing for any variable. Sure if we get all of them out. Yeah, there's an x there that those subtract out just like the 2's did. That x still multiplies that delta x. And then here, did I miss something? I did miss something. What did I miss? Oh. Yeah, I did miss something. I apologize. This is gonna be off. Let's see if it still works. I'm just gonna do the algebra here. So this would be x squared plus 2x delta x plus delta x squared. So that's what that would have been. That's where I made a mistake. So then this top part here is going to be, again, kind of did this on the fly, wasn't expecting to do this, but it will work. All right, so that piece,
That is actually X squared. Because that eventually cancel out.
we'll find out. Let's see. And then, yeah, this right here, when you plug in x into f, you're correct. This is going to be an x squared, right? You plug in x there, it'll just be x squared, right? Those x squareds now go away. And we're left with that, right? Subtract those out, we're left with that term. Factor out, the 2 there now, 2 there now, and then finally 2x. So for any variable x you put in there, it's going to be 2 times that value. So we asked at 2, 2 times 3 is 4. Okay. If we want to know the derivative of that function at 3, it's just 6. It's 2 times 3. And again, there's a very simple rule to do this for polynomial functions like that. And we'll get to that next time. I think my leg has had enough, and I'm not ready. Well, we haven't covered enough for us to discuss problems together. I need to introduce those formulas first, and then we can spend like half the next class doing problems together. So Zoom people, try to make it next time so we can do problems in class. All right, I'm going to stop the recording now.